All right, why don't we get going? Hello? Can you hear me okay? Yeah? All right. Oh, well. Welcome. We are almost done. We are happy or sad. Boo, yay? Which is it? Correct answer. What's the correct answer? Both. You are both. You're happy because class is over, and you're sad because what? Class is over. I guess that's true. Yeah. Okay. That's mostly you're happy because you've gotten through something. Remember when we got together so many months ago? The weather was miserable. It was cold outside, and you knew nothing about operating systems. Now, it's warm. dot, 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 dot. We will leave it at that. The rest is up to you. Okay, so what are we going to do today? Today what we will do, unfortunately we will cover some more material because we have time together and we don't like to waste that time too much. So we're going to cover a couple more things in the last area of class. Remember we had virtualization, we had concurrency, and we had persistence. Getting towards input-output more generally, but mostly focused on file and storage systems. So we're going to finish this topic today. And we're going to talk first about a particular file system called LFS, which stands for the Log Structured File System. This is a different way to build a file system that has been quite influential. So we'll learn about that and what problems it's solving and some of the neat things they do in there. And then we'll pop down a level and we will talk about not hard drives. In other words, we'll talk about flash-based solid-state disks, or SSDs, solid-state devices, really. Talk about some of the inner technology there and how they work. And we'll do that from not the level of a double E, of course, which starts at transistors and device physics, but we'll do more of a functional model of how an SSD works, which eventually leads towards computer science-like things that you would need to know if you care about storage systems in the least. Certainly flash-based SSDs have become very pervasive, increasingly pervasive, and therefore it's worth understanding them. Both of these actually, interestingly, will use a logging kind of technique. We learned a little bit about one type of logging, write-ahead logging or journaling, in order to deal with crash consistency in a file system last time. Here we'll learn about logging as a performance-oriented technique, as well as some reliability for an SSD, so we'll see how that affects. So that'll be the material, and we'll really just try to get through all of that today so we don't have to do any more material. Then we will have the end of class, so the end part of class. We will just try to end today with what do we end with? What should we end with? Words of wisdom, I suppose. So what does that mean for you? That means the ending sounds great, and you hope I skip through all this other stuff more quickly. For me, it means between now and the end of class, I need to come up with some words of wisdom. So hopefully that happens as well. But hopefully I have maybe at least what this will be. We can guarantee that there will be words, and then you can decide whether this part is apt. Okay, and then somewhere in there we'll do some other stuff like figure out how class is ending and all that sort of stuff. So we'll do that right near the end. Probably around here we'll do class maintenance stuff, admin. Okay, great. And I'm recording, so great. And now we can start talking about log structured file systems. So let me write that down. Log structured file systems, or a log structured file system specifically called LFS. LFS was developed actually in the time of hard drives. Yes? Oh yeah, sure. How's this? Is that better? Okay, thank you. So if you missed anything, we're talking about LFS, we're talking about flash-based SSDs, and then I'm ending class with some sort of final words. Okay, so then we're going to talk about log structured file systems. The motivation here was pretty simple. The motivation came from the world of hard drives. So And really, hard drive performance was a major motivating factor. What about hard drive performance? Well, when hard drives do well, if you think about their performance, when they do poorly, they do random IOs. These go poorly because they have seeks and they have rotations. Seeks and rotations, or any sort of what you would call mechanical positioning, is expensive. Now, to some extent, we dealt with this. We talked a little bit about locality last time. If you remember, we talked about this one file system called the fast file system, which tried to basically structure things on the disk, lay out files on the disk such that you would maybe minimize your seeks. So FFS, if you recall, what it did, it took the disk and it chopped it into groups, and maybe there's many groups, so this is a group. And then it tried to, say, put related things in a group, and then conversely spread unrelated things across groups, right? So instead of having a file in its inode or a bunch of files that are in a directory spread across a disk, we would instead concentrate those, say, on one particular group, and in doing so, we would reduce seek and rotational costs, perhaps, but mostly seek costs. But the problem there is it doesn't mean that you're avoiding random IOs. It just means when you're doing them, you're probably doing them slightly more efficiently. So when you read an inode, for example, to see where information about a file, and then you read its data blocks, which are nearby, you have a short seek, which I'll point to here, but it still nonetheless is a seek between those. So if you're accessing those all the time, you're still spending a lot of time doing positioning, and it means you're not spending time delivering bandwidth to application. What we also know from hard drive performance is, conversely, as opposed to random IOs, and really what I'm saying is random smaller IOs, if we do large IOs or large sequential IOs kind of all together, these tend to perform well. So if we could just structure things such that we always did very large transfers from a disk, and this actually turns out to hold for SSDs. We'll talk about SSDs at the end. If you want to get best performance, even out of flash-based SSDs, giving them large chunks of I/O is going to be effective. So everything we learn about the log structured file system turns out to be useful, even though we're going to change the technology underneath of us. So we want to figure out how to do a large sequential IOs as often as possible. That's how we get good performance. So now we have a bit of a problem, though. What's our workload in general? Well, it consists of reads and writes. Reads and writes. And we have to think about those a little bit separately. To some extent, we should think about this. Which of these, if we said we wanted to do all large sequential IOs, if we wanted to make all of our reads from the file system, like when we're accessing files, very large and sequential, what would we have to do? How would we cause that to occur? Remember, it's an arbitrary user of the file system. So how would we cause the file system to always transfer large blocks, large amounts of data from the disk, from a consecutive portion of disk, given that the user's workload might be arbitrary? They might read file A, B, then C. What would we maybe do? Yeah. Yeah, so that's a good suggestion. The suggestion is we can, instead of every time a read comes into the system, issuing it to the disk, what we can do is kind of batch up a bunch of read requests and then issue them to the disk. So that gives the disk, that will improve performance. Why will that improve performance of a hard drive? Giving it many requests to work on instead of at a time, instead of one at a time. Why will that improve performance of a hard drive? In a word, yeah. Yeah, hard drive scheduling, right? We could schedule those requests and kind of go through them in some sort of optimal order. But will that necessarily make all the requests contiguous, like one big block instead of spread out? And the answer, you can see by the way I asked it, is no, it doesn't necessarily do that. So reads, you'd have to get a little bit lucky. It's hard to make sure, hard to ensure that all of these are large, contiguous reads. So we're going to have to deal with that in some other way. Writes, on the other hand, writes are a little bit different. Because writes, we have a choice when we write something out. What kind of choice might we take advantage of when we're writing out data? What choice could we make that makes it so that, in fact, we can turn all of our writes into sequential writes, or large contiguous writes? What could we do? Let's say somebody is writing a little bit of data to this file, a little bit of data to that file, a little bit of data to a third file. What could we do to ensure that those writes are really, really efficient? In other words, large and sequential. Or could we? Is that possible? Yeah. Yeah, great. So the suggestion is we have some control where we're writing things to, right? For example, when we have a disk here, if somebody says, oh, write out part of file A here, let's say we have in memory here, this is memory up here, this is the disk down here, we have a block from file A and a block from file B and a block from file C that we need to write. Well, just go ahead and commit them all to the disk in one contiguous part of the disk, A, B, C. And then realize that that means that if we overwrite that file later, let's say later somebody writes a new block, A prime, instead of forcing it to be written here, in fact, let's say we were overwriting A and B and C, instead of forcing these writes to go into a particular part of the disk, what we can do is simply write them out to a new part of the disk. A prime, B prime, C prime. And then what we can do is update some sort of structure that tells us where the latest copy is. So that's going to be the generic insight that we're going to use in log structured file systems. The insight is that we can write data anywhere that we want, as long as we figure out how to point to it or find it later. It's kind of an obvious thing once you think of it, and we're going to take advantage of that today. The way we're going to deal with the read problem to the extent that we can is, and this was argued even in the original LFS paper, which came out in, 1991, the read problem we're going to deal with by simply hoping that, well, realizing that memory has gotten larger over time. At the time that the LFS idea actually was created, a typical desktop machine had, so let's say like early 1990, main memory. It was the same technology at that time, but a main memory on a desktop, like on a powerful workstation, like when I showed up in graduate school all those thousands of years ago in the early 90s, how much memory do you think a desktop machine had at that time? 4K. Not that bad, ballpark.
512 meg.
Yeah, not quite. I was pretty excited because my machine was one of the first to have 1 megabyte of main memory. It's pretty exciting. And I couldn't imagine what you would do with all of that. And it's still amazing to me how much memory we use. Of course, flash forward to now. Now, of course, we can see, regularly we see many gigabytes on your desktop. Who has a really high-end system with a ton of memory? Anybody? Yeah, how much memory? 32 gigs? 64? Anyone else gonna claim they have more? Okay, certainly many gigabytes. 128, I think. And many gigabytes, and even in like the Amazon cloud, you can rent machines that have like a terabyte of memory. It's an unimaginable amount of memory. Why does that help us with the read problem? Yeah. Yeah, because caching, right? Main memory is a cache for file data too. And by the way, that's something that will of course confuse you, is caching is used, the term is just used so generically in computer systems. The OS caches pages from files or blocks of files in main memory. Then when you access those on a processor, of course the processor has hardware caches that it uses to cache blocks or lines, cache lines at a time, 64 bytes, 128 bytes, etc. Right? And the compiler is even smarter. It knows what data it really wants to access and essentially caches those in registers explicitly. Right? It's happening at so many levels of the system, and smart applications do it themselves as well. But what it means is, if you think about larger memories over time, right? Larger memory, so this is time, this is memory size, and like we've seen, this is has gone up pretty fast, pretty exponentially. But what it maybe also means is that if you look at disk traffic, the percent of traffic that is related to reads, maybe that is going down, right? Maybe this is, so like read traffic. I can't write in italic. Sorry, that looks bad. Let me just write like this. This is like the percent of, say, reads versus writes. You could imagine that if reads are effective as a cache, that what they're doing is they're filtering that traffic to the device underneath, and it means relatively, the writes we still have to do, because the writes we want to persist the data. We want to make sure that we don't lose that data. So we have to do the writes even if we're efficient and we batch things and so forth. But reads, we maybe can get rid of a lot of them. Of course, the first time we read something, we can't, and if it gets kicked out of memory because we really don't have enough, we can't. But that was the argument. So the argument was that eventually all storage systems would simply focus on writes because write performance would be the dominant thing. Okay, any questions about that? Make sense? Okay. So what we'll do now is just talk about LFS and its basic structure, the log structured file system. This log structured file system, like I said, was brought into existence in the 90s. There was actually a great deal of controversy around it when it was created. So a bunch of papers that went back and forth. It was actually one of the first internet flame wars was over that in the modern era of the web was because of LFS performance as compared to classic file system performance, with professors at Berkeley and Harvard each claiming the other was kind of an idiot. If you're really industrious, you can find these old web pages somewhere in the web archive. Anyway, that sounds about as exciting as it is actually. Maybe you probably won't spend a lot of time doing that. But the performance of it was controversial, and we'll talk about why that controversy exists or what actually harms LFS performance. So for many years, it was viewed as just an academic idea. Then, more recently, as actually new technologies came into place, these kind of basic ideas turned out to be more and more useful, and the costs that we'll talk about kind of went away, and so the influence has become larger over time of this basic idea. Okay, so what we're going to do now is we're going to describe the structure of LFS. So I guess I already wrote LFS. We're going to talk about really what we're going to think about are its data structures. And like we said before, then we have to think about access methods. And what we'll think about here with the data structure piece is we'll think about, mostly we want to keep our kind of same structures that we have as before. So let me, I guess I'll just erase this, or sorry, I'll move this down so I don't have to write it again. So mostly what we want to do is keep the same kinds of structures, like for example, inodes, and inodes point to data blocks and things like that, and directories. All of that sort of thing we want to keep more or less the same. But we have to add a little bit more. As we said up here, as the idea that we had of with writes, the way we're going to make them be efficient is we're going to kind of be willing to write things to a new location every time we write them. We need some extra structures to tell us where the latest copies are. So in that sense, we're going to mostly keep them the same, plus we're going to add a few new structures in order to help us find things once we've written them to disk. Okay, so that's how we should kind of think about it. Then where we're going to talk about the access methods, really talk about when we're doing writing and reading, what we're going to see is what's different from our kind of traditional file system. Okay, so that'll be the basic idea, and we'll just kind of build this up one step at a time with kind of a simple example. Okay, and please feel free to interrupt as we go. So here's the basic idea. We know that we need to be efficient, we want to do large contiguous writes. So the basic idea is going to be very simple. First, we're going to buffer. Let's just focus on writes for now, and then we'll talk about how to read later. We're going to buffer many writes in memory. And in LFS terminology, we'll say that we do that into an in-memory segment. That's another one of those CS words that's used in lots of different contexts to mean lots of similar things. We're going to see an even further abuse of CS terminology when we talk about SSDs. SSDs talk about things like blocks and pages in ways that we haven't so far, and it's very confusing if you're not paying attention. That's just life. Here, a segment is a very simple thing. It's something like that's a few megabytes in size, and we're just going to define it to be big enough so that if we fill it up with information that we wish to write to the disk, and then we write it to the disk, no matter where we write it to, the time spent transferring it to the disk surface will dominate any sort of seek and positioning cost that we might have. So we just want to amortize the cost of a seek and a rotation by making this very large. The larger the write, the better. And so we're going to buffer a bunch of things in memory and then write it out. So step 2, then write to the disk. And then, of course, the key question is, what do you have to write? Sorry, let me write that a little bit differently. What to write in order to enable later reads. And then we're going to see what other problems we introduce as well. That's a question mark. Okay, so let's start thinking about writing. Sorry, I'll keep that on the screen. Writing a file out. Okay, so let's do, this is our example. And what we will do then is think about, we always will think about this as up here what's in memory, and then eventually what we're committing to the disk down here. Pretty simple idea. So we're writing a file. A file may have a number of data blocks in it. Let's say data block 1, data block 2, data block 3. Of course, that seems fine. And let's say we're buffering this in memory, and let's say we have enough data at some point, and we're going to then commit it to the disk. Okay, so data block 1 comes down here, and data block 2, and data block 3. So that's not too exciting. If we just had data and that's all we had and we didn't care about anything, what's in a file, this is what we would write. But of course, we know we have to write more than just data blocks when we're writing something to a file. So immediately what we think of doing is, of course, part of what we're writing is, say, an inode structure that's going to tell us for this file where its different blocks are. So let's say we have an inode here, and I'll just pretend for simplicity that this inode is 1 block in size, but really inodes are pretty small compared to data blocks, right? Inode might be 128, 256 bytes. Data blocks are probably, typically these would be 4K. And of course, we would buffer many more of these, but I'm not going to draw 4 megabytes of data blocks. This inode, in turn, is going to be written down to the disk here. And if you remember, inode has a bunch of information in it, like, oh, who owns the file, when was it written, and so forth. But it also has, importantly inside of it, it has a bunch of pointers or disk addresses which tell you where each of the data blocks are. And in this case, we're just going to write them all together. So whenever we have an inode, right next to it are the data blocks that it just wrote out, for example, when you initially write it out. So we buffer a bunch of stuff in memory in one of these LFS segments in memory, just big chunks of data, and then at some point we decide to write it out, and this is what it's going to look like. So any questions about that? Does that make sense? Okay, so then later, let's say, we come along. Now we have a few problems here, but let's introduce this problem. So later, let's say what happens is that the user overwrites, let's say, the second block of the file that we are writing, that we have inside of this file, right? The second file block. So this one right here. Let's say later we want to overwrite this. In a traditional file system, which we would call kind of a write-in-place file system, like every file system we've talked about so far is essentially a write-in-place file system. What we would do is simply, when somebody wants to, say, write D2, maybe call it D2 prime, what we would do is we would just update it in place. Of course, that's the problem we're trying to avoid, because if we're just doing updates in place, that means we are completely at the whims of the user. The user, once they've laid out their data, then can do writes all over the place, and those writes will go slowly because they have these incredibly high positioning costs, et cetera, et cetera. So what we're going to do instead is, well, when we write D2, we're going to, remember we have memory here, and we are going to buffer that in memory. And maybe there'll be some other stuff that we buffer to in our in-memory segment. And because we're writing D2 again, we're also going to write an inode again, this same inode here. But now with the second pointer is going to refer to this data block and tell us where it is. And if we think about the disk, well, let me go ahead and copy this piece here. If we think about the disk here, what's on the disk already, if we think about what's down here, well, we already have a bunch of stuff, right? We have the old version of the file, essentially. Now, what we're going to do is this is going to be written somewhere else. Because we never overwrite in place, we always write to a new location in one big chunk, which means over here what we're going to get is what we are calling D2 prime. And over here is what we're going to get is this new version of the inode, which maybe I'll just call I prime. I prime, of course, refers to this block, but because some blocks of the file have not changed, that means that I prime refers to them as well, right? Ooh, I don't want that. That was kind of cool. So I guess this makes straight lines if you hold it or something. Yes. I should have been doing this all year and all the lines would be so perfectly straight. How awesome is that? How? And of course I should have done this in a different color. So I'll just do it really quickly and I won't do the straight lines again because that's annoying. So the new pointers here are kind of green. The new pointer is green. And what we'll do is kind of highlight that the old pointer, it points to the same block, but let's use I guess I'll just use green for that. We're going to point now to this, and this is going to point to this as well. So you can see what's happened. What's happened here? We overwrote a particular block of an existing file. In order to do that in LFS, what we ended up doing was we ended up creating a new version of the inode. So this one is the old inode. This is the new inode. And this, you can see, is the old version of the data. And this over here somewhere later in the disk, and the disk is very large, this is the new version of the data of D2. And then these are just the existing versions. D1 and D3 haven't changed, so we just leave them in place. So when we're writing and we're overwriting pieces of a file, all we're doing is updating the pieces that we need to later in the disk. Anything that doesn't change, we kind of leave in place. And over time, you can see you have many versions of a file kind of getting created. Now, why? Of course, there's going to be some problems with that. Yeah, question. Yeah, the reason we're making a new inode over here is because something changed about the inode, right? And what changed is this piece right here, right? We have to record that somehow. And the easiest way to do that is just to write a new version of it and say, okay, now this part changed, but of course the other parts are the same. Oh, great. That's a great question. So the question is, we had written this file, let's call it the file version F, and then now we're creating F prime over here. And when we're creating F prime, it's kind of implied that I have the old inode. If I didn't have it in memory, that means I had to read it. I'm going to assume for many cases here, because of our what we'll call our large memory assumption, right, which we talked about here. Our large memory assumption means generally everything that we need will be in memory if it's old. We'll just assume that. You're right, though, that if we didn't have that, we would have to go and read it and then kind of write it out again. So that could be expensive if that happened, right? It's a good observation. Other questions about that? Yeah. Um, I don't know what you mean by the same place. So this is like the disk in from addresses, let's say I'm trying to represent this from addresses like 0 up to say whatever the max of the disk is. And so when I'm saying that we wrote uh, this part of the file out here, right, then we wrote it to like addresses 10 through 14 or something. Then when later we wrote the file, we wrote it maybe to addresses, 20 and 21 or something like that. So we're just kind of moving through the disk, writing newer and newer versions of this file. Does that answer your question, or does that make you want to ask a different question? Or third option, makes you hate what I said. Or fourth option. Okay, think about it, ask another question. Another question here.
So in that case, basically the inode file will be in another block, right? Because we cannot, basically we have to through the inode block. Right. So we should have passed on the place where the inode is.
I don't understand your question really. Right now we're just looking at this kind of logically. So we have addresses that we write things to. What I'm saying is everything we kind of need is in memory, including old stuff that we wrote before, perhaps like the old version of an inode. And then we're just writing out a new version of it to a new location over here.
Yeah, I'm just curious how the new inode and old inode is placed relative to
How are they placed relative to each other, this inode and that one?
yeah, on the
Yeah, I think all we know right now is this could happen much later. So you could have written a lot of stuff, so it could be very far apart. Or it could be very near each other because you're repeatedly overwriting the same file, right? So it could be either way. We don't know. All we know is that later when we write, we kind of buffer up a bunch of things and write maybe a new version of something. So they could be far apart. I think your point there, perhaps what you're getting at, is that means that an inode could be very far from some parts of its data. Right? It could be that there's some old data that was written a long time ago and you never update that, but you keep updating other parts of the file, and it means the file gets spread across the disk. That's true. We kind of don't care because when's the only time you would care about that? You would care if you're reading it and it's not in memory. We're going to assume generally files are in memory, so we don't care about read performance. We just care about when we write, does it go to the disk efficiently? That's the most extreme version of LFS. Of course, it turns out not to be quite true. There are cases when you read. Yeah. Yeah, no, that's exactly we know where the old inode is. In fact, we know where the old data is. So we could just overwrite them. But then we're doing two small writes that are separated by block. And if we have a bunch of files that we're doing this to, we're then creating a bunch of little IOs, which are very inefficient, right? They're just naturally inefficient. When we have to assume that what we're trying to do is write out a whole bunch of stuff together, all sequentially, all contiguous, that's when our disk will work as well as it could work. And like I said, it turns out that that's true for, for SSDs even for very different reasons. But that's what we're trying to do. We're saying, what if we wanted to write to disk? I'll get to your question in a second. If we wanted to write to disk so that we never had to like skip over little blocks or anything like that, we just always wrote contiguously. That fundamentally implies that we can't overwrite things in place. We have to write them to a new location. We buffer them up. We write everything to a new location. And then we have this problem, which is, well, we're going to get to in a second, but we have all this old stuff around the disk. We're going to have to figure out what to do with that. Yeah. Yeah, great. So the question was about bitmaps and allocation. We actually haven't talked about how in an log structure file system we do anything like that. So I haven't even introduced a bitmap yet, and we don't have a bitmap by and large. So for now, we don't have anything like that. We'll talk a little bit about how we manage space in LFS a little bit towards the end. But there's no bitmap here. We're writing inodes and data, and we're going to add some more sophistication in a second. Good question, yeah. Good to have some questions here so I don't get too far ahead of everyone's thinking. Yes? There are two versions of the same inode, correct?
But on the disk, there are two separate things.
Yes, that's correct. Yeah, great. So that's, yeah. The question now is, well, we have some problems, right? Problems, which is how to find the latest version of an inode, right? Like we want to read, for example, in this example, we want to read I prime, not I. So that's one problem. And what's another pretty obvious problem? Let's say we're writing to the disk like this. So we start at the beginning of the disk when the file system is created. We start filling it up with data. What's going to happen pretty quickly to this disk? Yeah. Yeah, we're going to have old inodes. We're also going to have a lot of old data, right? Every time we overwrite data, we're going to have old data that was left in place. We're going to have a term for that. It's called garbage, sadly. It's called garbage, which means old versions of inodes, old versions of data lying around. So what to do about it? That's going to be another central problem. We're going to address both of these problems, and then we'll have a sense of how an LFS works. Why don't we just kind of get through that, and then after we get through some rudimentary form of this, we can maybe take a break. So let's try to answer some of those questions. How to find the latest version of an inode. Okay, so how to find an inode, the latest one. So we're going to start with a simple construct. But we're going to create a new structure. Let's call it in memory. We'll call it the inode map. So you can think of it as this very simple thing. It has, I mean, you can think of it even as like an array if you want to. It doesn't have to be. It could be any sort of data structure. An array which, for each inode number, it tells you its location of the latest version on the disk. Okay, so if we go back to our example here where we had just 2 versions, I'm going to rewrite this example down here. So let's say we had this file F, and we had, of course, written F down here first to these few blocks here. So this is the inode of F, and this is data blocks 1, data block 2, data block 3. Then what our IMAP would say, let's say this is at certain locations, block 10, 11, 12, and 13. The IMAP would say, and let's say file F, we know the low-level number of that was inode number 100 or something like that. What the inode map then, or IMAP would say, is that inode 100 is located at address 13, right? It would tell us for this inode number, this is where it is. And again, this is in memory, just for now, and this is on the disk. Okay, so in memory, we have a structure for any inode number. It's going to tell us where it is. Later, when we rewrite block 2 and write D2 prime, so later we write I prime, which refers to D2 prime, and as well as referring to D1 and D3, what we would do at this point, let's say this is at block 1000 and 1001, what we would do is simply update the IMAP to say where the latest version is, 1001. Okay, simple idea. Just keep track of, it's just a level of indirection, right? Very common kind of CS thing to do, add a level of indirection, say this is where the latest version is. So that seems like not a bad idea. This inode map or IMAP is going to tell us that, and it's in memory. And it's actually not that big. If you have, millions of inodes active even in a file system, you're just talking about like 4 bytes for each, tell you where each one of them are. Not that big of a structure. So there's a couple problems we need to deal with this. It means that when we're doing reads, well, how do reads work? Well, remember when we open a file, like what's the directory contents look like in this file system? We haven't looked about directory contents. But directory contents are going to be the same as all the file systems that we used before. So directory contents tell us things like a low-level name like file F, and it tells us something about it, like file F has a certain inode number, like 100. This is the inode number or low-level name of the file. So the directory contents are the same. So when you're looking up a file, when you open it and you eventually get to oh yeah, F, and it refers to inode number 100. To then read that inode, you just have to do one more step than you used to do. You have to first then look in the IMAP and see where the latest address is so that you go to the correct version of the inode. So reading actually, assuming the IMAP's all in memory, is essentially identical, just one more memory lookup, which is fast, compared to, say, like a classic Unix file system that has a fixed structure of like here where the inodes are on disk. Before, when we had like the very simple file system, remember we talked about the very simple file system before? Very simple file system had a super block. It had some bitmaps here, which we're going to ignore for now. And then it had an inode table here. If somebody told you to read inode 100 from the very simple file system, how would you know the disk address? What would you do? It's just an inode table. It's an array of inodes. So what do we need to know in order to read the inode from the very simple file system, inode 100? What do we need to know? Yeah. Well, superblock data to tell us where this is, yes, and let's say we know that. But then what does that tell us? It tells us the location of the inode table. We need to know the size of the inode, each inode, and then we can just calculate, right? Like the base plus the index, which is the inode number, times the size of the inode, and that tells us exactly where inode 100 is. It's like right here. It's really easy to know where it is. In LFS, it's a little bit harder, but not much, because what we need to do is simply say, when we have inode 100, look in the IMAP and figure out that tells you where that is, and then you can go ahead and read the inode. So as you go through any sort of lookup for a particular inode number, whether that's a directory or a file, you just look in the IMAP to see where that thing is, instead of having a fixed location on the disk like we've had so far. Questions about that? That's really important to understand that. It's just one extra step, but it gives us all the flexibility in the world in order to read from anywhere, or find the latest version of the inode, and therefore we can write it anywhere. Questions about that? Okay. So but we have one more question, which is, well, we have this inode table. It's in memory. What are we worried about? What could happen? Yeah. We could crash, right? We could crash, and that means we lose the entire inode map. So it means we're going to probably think about, we need to figure out something about persisting the inode map as well. There's lots of ways to do that. So we could crash, and that would mean you would lose the inode map. So some options to deal with that. Well, what are some options? How could you deal with that? Let's say you wanted to deal with that. Let's say somebody said, yeah, this is how this works so far. Every time we're writing out a file or a directory, actually, you always write to new locations. You keep this inode map in memory. Then you basically crash, and you have to figure out how to deal with it. What could you do? What are some ways you could fix that problem? Yeah.
Flush the inode map with the raw function so that
Yeah. So one thing you could do is you can write out pieces of the inode map as you go. That's going to make sure it's persisted. And we're going to have to figure out how to do that. And that's going to turn out to be the solution that was taken in the original LFS paper. What's a different option? What else could you do? Instead of kind of writing out pieces and then kind of figuring out how to recover them, what else could you do? Yeah. Yeah, like you could essentially scan the entire disk and find the latest versions of each inode, and then use that to rebuild the inode map. Right? You could just scan through the disk, and if you somehow had enough information on the disk, you could say, oh, this is inode at time t. This is that same inode at time t plus 5. A later time, we would take the latest one that we find and kind of do it, put it into our inode map, and then we would just be able to run. So we could pay a scan. So what we're going to try to do instead is kind of write out pieces as we go. That turns out to have some efficiencies for various reasons, which maybe we won't get into in a lot of detail. So what does that mean? That means when we're when we're doing writing, what we're going to do is we're going to buffer in memory. Remember all those writes, like D3, D2, or whatever. I guess I did it the other way before. It doesn't really matter. D2, D3, and inode. And then what we're going to do is write out a piece of the inode map along with this memory segment. So this is what we buffer in memory. Then we're going to commit this all to the disk at once. So here's our disk, and we're going to commit this down here. But we still have a problem, which is we don't know how to find pieces of this. We don't know how to find pieces of the inode map because they're now scattered throughout the entire disk. So we're going to do one more thing, which is, let me keep that on the board there, quote unquote board. What we're going to do is periodically, what we're going to do is write out one more piece of data, one more data structure. And that data structure is going to be called the checkpoint region. A lot of information here. And what the checkpoint region is, you can think of it as being, here's our entire disk right here. The checkpoint region is kind of like our super block in our existing file system. And what the checkpoint region has in it primarily is it has pointers to pieces of the inode map. So this is a little piece of the inode map piece here, inode map piece here. Let's say piece 3. This is inode map, some piece of that array, inode map piece 100. The checkpoint region points to all those pieces of the inode map. If you start at the checkpoint region, you can then read all the pieces of the inode map into memory. Then you have the in-memory inode map, and then you can be kind of up and running. So what does that mean for our writes? We buffer everything in memory, including the location of this inode, that part of the table that tells us where this inode is. We just write those out to segments. We fill our disk as we go like this. And then periodically, once in a while, we update the checkpoint region, the topmost structure on this file system, to tell us where those pieces of the inode map are. Once we know where those are, we can use the inodes to read file blocks in the exact same way as before. So it's a little bit complicated. Why don't I take any questions on that? And actually, let's take a break at this point. Yeah, a few questions. Yeah, exactly. So that means that will be like old pieces of the inode map will also be there. We still haven't dealt with how to deal with garbage, but absolutely one piece of garbage was data, another piece of garbage was like old inodes, and now we have old pieces of the inode map which give us a previous version of those inodes, and we have to figure out how to kind of reclaim those as well. So that's true. What else? Again, our goal just to write everything large and sequential. Turns out to be a little challenging, but we can do it. Yeah, you could periodically write out the entire IMAP. What that means is instead of writing kind of pieces as you go, what it means is you're kind of longer and longer, you're kind of making it so it's going to be hard to recover the information that you're like. If we write pieces as we go, it turns out after we crash, it's kind of relatively easy to recover those and then find stuff that we had written, say, in the last 30 seconds. If we don't do that, that means it's going to be more work for us. So we'd have to record other information. I mean, you could do it that way. It wouldn't be crazy to do it that way. It's just kind of simpler to do it this way so we can recover things more quickly. Other questions? Okay, so hopefully you have a sense of how this works. It may not be perfect. Why don't you take the break to think about it, and then we'll come back and talk about it.